And so I first made some models of such channels by using sampling, and you make a tap delay line model with taps at 1/2W. So you have, and now in this signal, if you put an impulse response into such a channel, you get a long signal which dies out effectively after some time. So there's a duration limit, and the signal has finite bandwidth, so you have a bandwidth limit. So I first made some models for such channels, which was interesting and people liked it. But then there came the problem, how do you measure the characteristics of this channel by putting an input signal of some kind, measure the output signal, and say what is the channel. So we have a model for the channel, which is a tap delay line with taps, each of which has a time-varying gain function. So very quickly I found that if you put an impulse every now at a regular rate, matching the Shannon constraint, you can the necessary condition I could find a sufficient condition for measuring the channel, namely that the product of the time duration and of the bandwidth W, that product should be less than 1 in the right units. Okay. So that's a sufficient condition. I had a simple impulse train for measuring. But how to prove that this condition is necessary? In other words, that even if this condition is violated, if the product is greater than 1, can you still measure the channel? So I tried for a few months, and at those days you met your advisor once a month or something, and he'll ask you what is happening. So I said to him, I have no progress, so please suggest some other problem for me to do. He said, okay, that happens. But you write down your result, why you are having difficulty, because that will help people to understand, what is the nature of the problem. So this is a message for students also. In the course of writing up why I could not find a necessary condition, I got a very nice idea which solved the problem. And the idea was the following. You see, your input signal has some degrees of freedom, duration and bandwidth 2TW. The output signal has a longer duration because the channel has memory, and it's time varying, so the bandwidth is more, so Doppler bandwidth. So the output signal has more degrees of freedom. Now, what about the channel? Each gain function has its own degrees of freedom. So you have certain number of taps, certain number of degrees of freedom for each tap. So my condition was that if the number of degrees of freedom in the input plus the number of degrees of freedom in the channel is less than the number of degrees of freedom in the output, then it works. If it is greater, then it's not possible. So, and you can make some matrix equations for this, and it's called underdetermined channels, or I forget now, underdetermined. So I was happy but I pointed out in my master's thesis one problem. Mathematically, if a signal has finite bandwidth, its duration has to be infinite. That's the Fourier theorem, actually. Or if it is finite duration, the bandwidth has to be infinite. So you cannot say that you have a signal of duration t and bandwidth w. Mathematically, it's not correct. But Shannon used the argument that effective duration t and effective bandwidth w has 2TW degrees of freedom. And in his famous 1949 paper on the Gaussian channel, he used this example. But I mentioned, and then people, Pollack, Slepian, and Landau use something called prolate spheroidal function, some of you may know, showing that if it's really reasonable, this 2TW. But I still said mathematically it's an open problem. But that was my master's thesis. And I got a job at Lincoln Lab for the summer because they were so happy. Now they found out that when the rake system did not work, when this product was greater than 1. So we use the notation underspread channel and overspread channel. That's what it is now, yeah. So now I had my master's degree at that time, and Bell Labs was recruiting very actively from all the universities. In the old days, Bell Labs was a very great lab. Were you at Bell Labs? Yeah. So they would send a recruiter to the campus to meet the students and so on. So they said to me, come work in Bell Labs, we give you a big salary, and people like Shannon and Slepian and Bodie and Shelkunov are giving lectures. You can attend those lectures, and you can get a PhD from Columbia. So why would you should get a student salary and so on? So I was tempted. But Wozencraft told Price and Green, the inventors of rake, that Kailath is planning to go to Bell Labs. So one day they called me and said, we want to have lunch with you. And they said to me, that's a good offer, of course, but the hardest thing about doing a PhD is finding a topic. Now you're lucky that this area seems to be a good one for you. So, you have a topic. Secondly, of this Price and Green, Price was the mathematician and Green was more the engineer. He said, and the rake system is actually based on certain ideas from Price's MIT PhD thesis of 1953. So they said, you can work with Price, so don't go to Bell Labs. So I agreed, actually. That was one of the lucky things. In my life, I had many lucky circumstances. I did not go. And in that summer, working with Bob Price, I essentially got the main results of my PhD thesis. But then I had not planned to stay for PhD, so I did not take any of the undergraduate courses at MIT, only took graduate courses. But in the first quarter, you have to take the qualifying exam. And at that time, MIT was very difficult. You had 8 one-hour exams, and if you did well enough in those exams, you had an oral exam of 3 to 4 hours with 4 faculty. Now they reduced the system, I think only 2 papers and so on. And somebody from physics, somebody from different fields. So they found out in the course of the exam, they asked me something about antennas and so on. And I did not know. Because in India, when I studied, we had only one textbook, Radio Engineering by Terman. Some of you who are older may know this. Everybody used in the world this Bible, radio. But it is more a cookbook type of book. Maxwell's equations are not mentioned in that book. So I did not know Maxwell's equation, the physics professor. So I said, okay. I had a friend, my classmate, very famous now, Shmuel Winograd. He's in computer science. He had in 3 years, he came as undergraduate to MIT from Israel, bachelor's in EE and bachelor's in mathematics. He also took the qualifying. He did okay in the orals, and he went to the exam. And one of the professors was in material science. So he asked, one of the questions was, how do you harden steel? When you make steel, you have a process to make it really firm. There's some metallurgy here. Winograd did not know. He said, I don't know, maybe you hammer it. So they said, okay, you failed. But what is the cure? They made Winograd and me the teaching assistant for the undergraduate course in electromagnetic theory. So we became experts at electromagnetic theory, because in those days the teaching assistant at MIT they had to know better than the professors. They had to make all the homework problems and so on. So we were quite good experts but now I've forgotten everything there. Anyway, but I passed the second time I passed, and I got this degree. Now, one important thing I learned from MIT is you had to write reports. and they had an English editor who would make sure that you wrote very precisely and correctly. And so that's very important, because you can have many good results, but if you do not explain it clearly and in a logical way, people won't read it. And this is one of the messages I try to inform my students, that pay attention to writing the paper clearly, with motivation, step-by-step explanation. Maybe proofs are not so important as the ideas. Give the proof in the appendix and so on. So there I learned one thing. Everybody in the world, Zade is starting with saying, time-varying systems. This English editor said to me, that's not correct. Because you have time-invariant systems. That means system which does not change with time. That's time-invariant. Time-varying means you are changing the time. Time-varying means you are changing. So you must say time-variant. That means changing with time. So I write always, and in my thesis, time-variant, but I'm a minority of one. Because everybody still says time-varying networks. But that message to communicate, and I keep telling my students the joke at Stanford, that you must be very careful about when you use which and when you use that. Generally, you should use which only after a comma. It's an explanation, but otherwise you should use that. So I was happy to say that I wrote lots of papers, and in the beginning, most of my papers were by myself, and I think they were good to read, so I got a reputation. And then I started to work with students, especially when I wanted to enter new fields. For example, Professor Kalaj was telling me that recently in their work on communication and control, they found an old paper of mine from 1966 on feedback communications. But that reminds me of a story, so let me tell you. I told you in my master's thesis, I said that my proof is not rigorous because this finite duration thing. In 2006, there was a paper in information theory transactions by two mathematicians, one from Germany and one from US, giving a rigorous proof of this condition. They quoted my paper and said, they praised it. They said the intuition is good, the result is correct, but the proof is not correct. It's heuristic proof. And they have a rigorous proof with the result the same, but without this assumption of 2TW. I could not understand the proof. You can see it's by Pfander and Walnut. It's too much mathematics. But anyway, they have now worked on it, and I work with them now, and 2 years ago we wrote a joint paper. I still don't fully understand the mathematics, but at least I give them the ideas. So why did I mention that? Oh yeah, so feedback communication, at that time satellites were just being put up. This was early 60s space communications. And in satellite communications, you can only have small power on the satellite, so the link from satellite to ground has noise. But on the ground, you can have very powerful transmitter. So the link from the ground to the satellite is almost noiseless. You can exploit that fact to find a very simple way of achieving channel capacity with feedback. And so we wrote that paper. It got a lot of attention. But it was never, and we said the application is space communication. It was never used. Because in space communication, there's a delay from the satellite to ground and vice versa, and that complicates the algorithm. But many years later comes network communications, and there the links are short, so the delay is small. So this algorithm is now used 50 years later quite a lot. Just as my result about overspread and underspread channels, a lot of papers are now appearing saying, suppose you do not know the bandwidth and the time, can you still have such a condition? And there are results. So sometimes it takes a long time for the result to be fully appreciated. So you should be patient. So in this feedback communication, you have to try to estimate the signal recursively. That means you get data, you have to, so here's the system. You send a signal to the transmitter from the satellite sends a signal to you, and it is corrupted by noise, so you do not know exactly what is the signal. So you send back on the noiseless link what you thought the signal was that they sent. The transmitter sees whether you are right or wrong, and he adjusts the power to increase it if you were wrong, reduce it if you were right, so that you eventually get all the answers correct. Okay. But what do? They estimate. You don't send the actual signal back. You are estimating the channel, and you send that information back. And when one new data comes, you change the estimate of the channel. So the estimation has to be what is called recursive estimation. And Kalman filter, many of you heard about Kalman filter, is a method for recursive estimation, and it requires not frequency domain method, but time domain state space estimation. I should also tell you the fact that my thesis at MIT used matrix theory. Hardly anybody in engineering at MIT knew what was matrix. In power systems, they had discovered, two professors, that you could get a unified theory of induction motors, synchronous motor. Nowadays, you people don't learn all these things. We had to learn different kinds of motors. I mean, in my education in India, we had to do engineering drawing, surveying, metallurgy, and so on. Now things are better. But anyway, what was I saying? Yeah, so they were afraid they wrote a book, they were afraid to use matrix notation, AX equal B. So they wrote out all the equations, A11X1 plus A12X2 and so on. Right. And my advisors were not, they say, your thesis is too mathematical, you're using matrix. Anyway, now everybody has to learn linear algebra. It's compulsory and using matrix. But it changes. I must say, when I went to JPL, I went for 1.5 years to JPL, and I attended a talk from the numerical analysis group, and there is a famous formula in matrix theory, which some of you may know. If you have a matrix capital A, whose inverse you know, A inverse, if you add some product of low rank, say add another BCD, which is low rank, what is the inverse of A plus BCD? There's a formula for this using A inverse. These people had discovered this formula, but they said in the seminar, we did not know how to prove it, but we verified it by hundreds of examples on the computer. So I went later to them and I said, the proof is very easy. But you know, the state of knowledge for engineers was so limited at that time. Anyway, so to study state space, we did not know at MIT about state space. And Stanford also, the control people knew about it because they were studying. But I did not know. But my students took the courses in control. So I said to them, Jim Omura, teach me. Because instead of going to the lectures, it's much easier to someone explain, and then I can ask him the questions. So I learned about Kalman filter that way. And I found, so he wrote his papers by himself later. But when I wanted to enter a new field, many years later I started to enter in VLSI, I told the students, let's learn together about VLSI. You read, you know, I'm busy. I have to supervise students. I have to teach courses. I have to write letters. I don't have time to study so much myself. You learn and you teach me. Okay? So we entered, and tomorrow I'll tell the story of that. It was quite successful in VLSI. We got good results knowing nothing. And my student Jagdish came, we had a reunion of my students last year, and he said, I learned that in research, the professor doesn't necessarily need to know more than the students. You see, you learn together, but the professor is more experienced, and you can ask. The important thing in doing research is to ask questions. And I say that when are you ready to graduate with your PhD? When instead of the professor asking you questions, you are able to make the questions yourself. Okay? That is sort of the threshold of doing research. How to, anyway, we'll talk a little more tomorrow about that. So I learned control theory, and actually I did a lot of work in Kalman filtering. So now that only takes me to a certain point, but I began to work with students. And we worked in VLSI, and using a combination of all the techniques that you mentioned here, I'll conclude with this story actually, because we have to wind up in 5 minutes or so.
It's unlimited.
Not time limited? No, you have to have dinner.
No, I think we got a message from Babak's wife that she's not prepared yet for dinner. So.
Okay, so let me finish with the story of VLSI. My student Sailesh Rao, VLSI has certain structures. You know, you have very regular structure of transistors, and the connections are local. Every transistor is only connected to the 4 neighbors. Okay? So how to use this structure to do signal processing? So his thesis was about VLSI architectures for signal processing. He went to Bell Labs. I took 3 students, by the way, for VLSI. We learned together, and 2 postdocs. And Bell Labs hired in 1 year all 3 students. And his boss, the recruiter, no other students in Stanford? Says no, each of these students did 3 theses by the time they finished. By the way, Babak not only worked on his own thesis using signal processing for defect inspection and pattern inspection, he also worked in communications. He wrote papers in communications. Because in our group, people worked in different fields. They listened to the seminars, and they wrote joint papers. So it's a help. So anyway, he went to work in Bell Labs, and this was the time when HD TV, high definition television, was very important. Because Americans found that Japanese were doing all the electronics work. Sony, Walkman, all this. Japanese controlled the electronics market. So how should America get into this? So high definition television should be the project. So a lot of money went into that, and Bell Labs was also working on HD TV. Sailesh Rao heard that the designers were not able to meet the specs of enough power and enough, you have to put area restriction and power restriction, and they could not meet the specs. These are designers with 10 years experience. So Sailesh said, in my thesis, I had methods for systematic design. And so he spoke to his colleague Mehdi Hatamian and said, let us work on this problem. My thesis can be relevant. So they asked their boss, let us spend time on this. Now, I don't remember exactly. In a few months, they found a design which met all the specs by far. I forget, like 2/3 of the area and 3/4 of the power, something like that. And there was a picture in the Bell Labs magazine of Sailesh with his design chip. So the theory became quite useful in VLSI. And to make the story short, so then the other people would come to them and say, hey, this chip is the next most important chip in Bell Labs. You please design for us. After they did 2 or 3 chips, they said, why should we do this on Bell Labs salary? Let us go outside and, then we can charge more. So their boss is a famous communications engineer called Lucky, Bob Lucky. You may see his name in IEEE Spectrum every year, every month. He writes a column called Reflections. Bob Lucky said, we promote you, we have given you the highest salary. If you leave, we are not going to give you any more jobs. 6 months later, they gave them the jobs. So anyway. So Anyway, so then we began to work with teams of students, and that's how we got into semiconductor manufacturing, and we made, tomorrow I'll talk more about those things. And I'll just conclude by saying that tomorrow it's a talk about, with a very presumptuous title, and I'll explain how the title came because I was bribed to give this talk, and I'll describe the bribe tomorrow. But I was thinking about, who makes breakthroughs? Only Shannon and Wiener and all that. But all of us make, Farouk and Babak, all of us make minor breakthroughs. So tell us about your work. So I'll tell. But the work I did by myself is mostly mathematical, and it's hard to describe to different audience. So tomorrow I'll talk about our work in little bit in VLSI and little bit in DSL, and more about semiconductor manufacturing. So thank you.
Okay, thank you.
Now I'm asking the audience, are there any questions, comments?
It's too general, but if you have general questions, you can ask me.
If you don't have any, yes, Abul Faz, go ahead.
Yeah, you may have to repeat. My hearing is not very...
Here.
So you have done very great jobs in many different fields. My question is, how could you manage to be very deep in all of these fields and follow all the students working on those fields?
Well, it's not an easy question to answer, but I must tell you that one of the things that I found very useful was, as Babak mentioned, to take ideas from one field into another. To cross-fertilize ideas. And that's a very useful and technique in general. Because I found that, for example, the difference when we started to work in control theory, in estimation, in communications, people use what they call Wiener filter, which relies on the solution of something, an integral equation called Wiener-Hopf integral equation. In control theory, they use state space methods, and the Kalman filter uses something called Riccati equations, which is a nonlinear differential equation. Control people don't know anything about Wiener-Hopf integral equation, and vice versa. In those days, communication engineers did not work with these things. But I found that by using the ideas from Wiener theory in the Kalman filter problem, we found ways of improving the Kalman filter. And if I may take a minute or two, the Kalman filter talks about, if you have state space models, the models can be time variant models. The ABC parameters of the state space model can vary with time, because the formula of the Kalman filter doesn't matter whether the functions are constant or vary with time. The computation is the same. But I was thinking, I said, if the system is not changing with time, there should be some advantage. Why should you not have some benefit from this? And I found that the Wiener-Hopf equation, which Wiener used for Wiener filtering, was actually invented in radiative, it came up in the field of radiative transfer. Namely, sunlight reaches the Earth by coming through the Earth's atmosphere. And there's multiple reflections. It's like actually a multipath. And so the Wiener-Hopf equation was produced there. And and there's an interesting story that Norbert Wiener, you may have heard cybernetics and all that, very interesting man. He had this habit, people ask him, he says, what is a new problem in your field? Let me think about it. So a famous astronomer called Hopf, H-O-P-F, went to visit him one day in his summer home. And Wiener asked him, so what